Okay, good morning. Just a couple of things before we start the lecture. Okay. The teaching evaluation is ongoing. The TA evaluation, you should also contact your tutorial TAs, because there are 3 TAs for each course. They asked me to ask you, to evaluate. They really think the comments will be very important for their future development. So take your time, do the evaluations. And of course, same thing to me too. Basically, the online evaluation turned out to be actually once online, the participation rate dropped quite significantly. Last year I had 190 students, and only 40 students did the evaluation. So once you learn statistics course, that's not going to be the right amount of sample, right? So the more the better. Okay, so that's evaluation. And the other is the formula sheet for 248 I uploaded already. Okay, there might be a slight change. I'm not sure, but if there's a change, just I'll let you know. Okay, but for now, the formula sheets are there, and so take a look at it to see what's missing and see what you need to memorize. Let's continue on the lecture. Okay, so this is a very important lecture, surface integral. Okay, so it's guaranteed there are a couple of questions out of this lecture in the final exam. But before we do that, let's just take a quick review of a couple of the operators we learned. Okay, first is the curl F. Okay, the definition of curl F is basically when curl F dot n hat equal to the limit delta A equal to 0. It's a circulation around a very small area. So that's curl F. And this turned out to be the same as del cross F, which is basically the determinant of this matrix. Now, in terms of calculation, it's not that bad. It's very simple, just a matrix here. But I need you to understand the physical meaning behind the curl F. So what it tells you, basically, right? If you recall that in the last lecture we mentioned, the curl F basically tells you is the circulation around a small area. Okay, and how is there circulation or not, right? If there is no circulation, basically 0. If there is a circulation, then there is a direction. So direction is given by the direction of this vector. Okay, so the curl F, sorry, I should write it here. So curl F equal to this. So this is a vector here, okay? The direction of this vector gives you this rotation, basically, the circulation of the direction of the circulation. Okay. And then we have this Green theorem. So the Green theorem that we were talking about, first of all, this is a 2D here case, okay? So basically, we focus on this Green theorem here focuses on the XY plane or ZY plane or XZ plane. Okay, so it's a plane. Then what happens is inside the plane you have a curve C. Okay, it's a closed curve C. Okay. So the closed curve C is in that plane. Okay. Then we have a vector field F, and this closed curve C generally we oriented counterclockwise, okay, which is what we call positive orientation. So you look at it from the top, okay. So this is a counterclockwise. Basically, when you do this line integral, okay, you do it, okay, counterclockwise direction. So the Green theorem basically tells you is you don't calculate this line integral anymore. You calculate an associated double integral. Okay. So this double integral is integrating over a region R, and the R is enclosed by this curve C. So closed curve C, okay, enclosing a region R. Okay. So this double integral, the region R is from the C there. So what are we integrating? We're integrating partial n over partial x minus partial m over partial y, okay, dA. So that's what we're integrating. So here, this f, the vector field, is a 2D vector. Okay, so it's mn in here. Okay, so that's Green theorem. So Green theorem, just remember, the key points. Green theorem deals with a curve, okay, inside a plane. It's a plane case here. So the natural question you probably should ask is, well, how about the curve in the 3D space? Well, what if the curve is like this, right? Not in the plane like this. Now that we have another one in the future dealing with this 3D case here, right? Yeah, which is next lecture. But this is a Green theorem in 2D though. Okay. And then we have this concept of flux. Okay. So flux is basically it's coming from the vector field. Okay, you have a vector field, and then you can draw, as I show you, you can draw a couple of lines, or cluster of lines, so we call streamlines here, to represent the vector field. So it's as if there is something flowing, right? Yeah. So well, actually there is. If there's a fluid thing, there is a water flowing, right? Yeah. So then flux is basically it's amount of something. Okay, it's amount of something passing through a surface. Okay. Okay, in unit time. Okay. Yeah. So this is the flux that is here, and based on this simple concept here, now this is actually, today we're going to talk about basically flux. Basically we're going to calculate how much, right? How do I calculate the amount of something through the surface? That's what we're going to calculate. This is what we call the surface integral here. Okay, so surface integral basically going to give us this flux calculation. Okay. But I think what I did is actually sometimes the order of the teaching sometimes is they talk about surface integral first and divergence, but I talk about divergence first, right? So divergence basically is called flux density. Okay. And in simple language, so divergence is essentially equal to the net flux, okay, over a volume. Okay, a delta volume, right? So that's divergence. Divergence. What divergence tells you, the physical the formula is del dot f. Okay, that's divergence. Okay, so that basically equal to partial f let's say partial m if f equal to m in p, right? Partial m over partial x, partial n over partial what was it? Y, yeah, and then partial p over partial z. So f is m n p. Okay, so this physical meaning behind divergence is it tells you whether you have a source or you have a sink. So it's basically the rate of change of this flux here. Okay, whether you have expanding lines out or you have a shrinking lines into it. Okay, so that's basically what divergence tells you there. Right? Yeah. So in terms of the fluid, then the fluid is flowing. Okay, and the rate of the flow maybe is different. So at some location, okay, it's going into it. At some other location, it's coming out of it. Okay, yeah. So that's divergence. Okay, and you look at this definition, divergence. The numerator here is a net flux, right? Net flux. So I have a sphere, okay, closed surface, okay, So what's the net flux out of this surface here, right? Yeah. Then divided by the volume, that give you this divergence, right? Now, this is basically a question now. How do I calculate this net flux? And that's basically how do we calculate this flux at here. So this is today's topic here, okay? So how to calculate this flux. That's today's topic. Okay, so to calculate the flux, I'll give you basically a simple example right here. Okay. So let's consider a very simple example. Let's say I have a hose at here. Okay. So water is flowing in the hose. Okay. And this cross-section right here has an area of A. Right? Okay. So let's say water is flowing at a constant velocity, V. And the V in this particular case is perpendicular to this A at here, right? Okay. So then the other quantity, I think, let's say the mass density. Okay. So maybe we have a mass density regarding this water. Okay, let's call it rho. Okay. So consider constant mass density of the water, right? Okay. So it's not polluted. It's good water. So rho, the unit will be kilogram per meter cube. Okay. And the V, of course, is going to be meter per second. Okay. So A is going to be meter squared. So then, if we're interested in the flux, basically interested in how much fluid passing through this cross section A in unit time, right? So then, how do we calculate? So we're going to calculate, this is basically so-called, we're going to calculate the so-called rate, okay, rate of flow, okay, of the fluid, okay, and that calculation, let's use the W1 in here to call this rate of flow of the fluid. So W1 will be what? Will be your mass density rho and multiplied by this velocity V. So the V at here is perpendicular to the A. So let's see the magnitude of V is, let's see this, okay? Yeah, it's velocity. So the rho multiplied by the V, and then multiplied by this A cross-section area, okay? So that'll give you this rate of flow of the fluid passing through that area, okay, like this. So the unit here will be kilogram per second here, okay? Yeah. So this is when V is perpendicular to A, right? Yeah. As a matter of fact, when you're saying, okay, something is passing a cross section, so basically what you're talking about is the something that you're thinking is actually that quantity of something perpendicular to that cross section, right? So this case is happen to be perpendicular. So now if you look at a slightly different case, if the cross section here, if I cut the hose like this, okay, so there is an angle now between this V and this A here, okay? So this is A. Let's call this A1 here. This is A2, okay? A2. So A1 will be this portion right here, right? This portion. So there might be an angle between these two. Let's call this theta here, right? Yeah. So now, if I wanted to calculate the same thing, then you'll calculate this. What will be the rate of the flow of the fluid? Okay, basically, what will be this amount of flux passing through the surface A2? Okay, yeah. So then what we're going to do is what? Let's say still call it W1 here. Okay, it's going to be rho V and A1, right? So really, what's passing through this A2? It should be the perpendicular quantity. So it's the A1 surface. That's what the surface part of the surface counts, right? Yeah. So it's going to be A1. Actually, it's going to be A2, right? Yeah, it's going to be A2 here, cosine theta. Okay, A2 cosine theta. Right? Or you can think of it this way here. Okay, let's say I use a n hat, okay, to represent the normal direction, the unit normal. The unit normal vector represent a direction of this area, cross-section area A2, right? Cosine A2. So what's passing through this A2? Right? Where's the V direction? V direction is this, right? It's this direction. So what's passing through the A2 is the projection of the V in the direction of which one? The N hat, right? That's basically here. So what's passing the A2 is should be V dot N hat. That's what's passing through A2, right? Yeah. Actually, if this one here, this is a quantity you write using an expression. If I use a vector to express this quantity, that would be what? Rho V. This is dot N hat. This is V dot N hat. Then multiply by this A2, right? So that's the rate of the flow of the fluid here, or amount of fluid passing through that cross section A2. Okay, yeah. So just think of basically the idea is you talk about something passing through the surface, then you need to look for what? Look for the projection of that something in the direction of the uninormal, in the direction of the normal vector of the surface. Okay, that's basically what happens here. Yeah. So this is a 2D, right? This is 2D. Now if I extend this idea to 3D case, let's say in 3D, I'll give you a surface. Right. Okay, so there's a surface right here, and there is a vector field, okay, in the 3D space. So let's see, I have vector field just everywhere. Okay, probably going to be pointing to different directions. And now we're interested in what is the flux? Okay, basically the amount of that vector field passing through this surface S right here. Right? Yeah. So what we do is we do similar stuff like this. So what you can do is you can take a very small quantity, let's say very small area around here, right? Very small area. So this very small area is basically you can represent that small area using a so-called area vector. Right? So in other words, at this location you have a normal vector, uninormal vector pointing normal to this small area and perpendicular to that, right? So let's call it N hat. Okay? Yeah. Then for this little area, maybe I'll use this vector here. So I use the area vector. I'll use the area vector dA here. Okay? Yeah. Use the dA to represent this small area. So it's a vector, then it has two quantities. One is direction, one is the magnitude. So the direction will be N hat. Okay, the magnitude will be just its area. Okay. Yeah. So if we're looking for the amount of the something passing through that small area, right? So what do? Basically, it's going to be F, okay, dot N hat, and then multiply by this small area dA. Does that make sense? No. Pardon me? That's a flux, yes. That's flux, right? So that's the flux passing through basically this small area in a unit time. Okay. Okay. And this is only for one little area here, right? And of course, if you're looking for the thing passing through the whole S here, the flux basically, okay, over the whole S here. So what do? We're going to have an integral, the whole thing, right, over this surface S here. Okay. Now the only trick here is when I use the integral here, so how many integrals should I add? Should I just double integral? Should I single integral, double integral, triple integral, or even more than that, right? So that's basically, sometimes the notation is just one integral, just this. But in this particular case, you need to think of this. It's a surface, right? It's a surface. If I'm looking for, let's say, when I'm learning double integral, so where are we integrating? We're integrating over a region R, right? Region R. So that region R basically it's part of the surface. So that's a double integral there, right? So this is S here. This is not a solid you're integrating. So this is basically a very thin surface here. So then the integral here is actually going to be a double integral. Okay? Yeah. So where are we integrating? We're integrating over this surface S. Okay? So that's basically the flux here. Okay? The total flux over this surface here. Okay, good. So now you look at this formula. What I need you to basically understand is a couple of the symbols here. What do they represent here? Okay, first of all, you need to always remember this n hat. Okay, represent is the normal vector, the unit normal vector to the surface. Okay, so the n hat here is a unit normal vector to S. Okay, to the S. And ADA is basically a small area on the patch, right, on the surface S. Okay, and F represents the vector field. Okay. F is the vector field, and it's in 3D space, so there's going to be 3 quantities. So each quantity is going to be a function of x, y, z. Okay. Okay. So that's what this one here is. Now, before we move on, actually, just think about this guy here. Then I'll talk about a couple of things here. N hat is the unit normal vector to the S. Okay. So let's say you have this surface here, right? Let's say we learned that z equal to x squared plus y squared. That's a surface, right? That's a surface. Okay. Yeah. So this is a surface here. And if the n hat is the unit normal vector to this surface, right? Aside from calculating this flux here, if I just ask you, what is the unit normal vector to this surface? How would you calculate? How do you, first of all, maybe before talking, how do you get a normal vector to a surface? Plane equation, but this is a surface here. What's the last question on the midterm exam? Derivative tangent vector. Gradient, exactly, right? Gradient. Yeah, gradient of that surface, right? Gradient of the function is perpendicular to the. So basically, you let w equal to z minus x squared minus y squared. Then this del w is perpendicular to where? To this surface. Okay? To the surface. So del w is perpendicular to the surface. So how do I get the unit vector? Exactly. Del w over its magnitude. Okay? Yeah, so that's basically something here. Okay? Yeah. Alright, so this n hat will basically is a del w over del w. Okay? Yeah. Okay, so now the only question here comes is, how do I evaluate this double integral, right? So what should I do to evaluate this thing here? Now, before we talk about the different cases to evaluate this double integral, there's one important thing that we need to see first. So that's basically so-called the direction, so basically orientation, okay, of S. Okay, orientation of S and n hat. Okay, yeah. So this is a concept that we're going to use also in the future in the next lecture, actually. Okay. So first of all, let's think of the same simple case here. If I have a surface, okay, if I have a surface, and then you look at one location here. So how many perpendicular vector to that surface at the location? How many direction? You have 2, right? Yeah, one could be pointing up, the other could be pointing down, right? Yeah. So now the thing is basically, which one should you use, right? Should you use this direction or that? So that's basically one thing we have to decide on. So generally, okay, actually for a non-closed surface, you can choose either one. Okay, you can choose either one. But usually we choose this upwards one, okay, as the positive one, right? Yeah. So basically, let's say for non-closed S, okay. So we take, okay, this n hat upward. Okay, we take the n hat upward. So what does upward mean? Well, this is a z. This is x, y, z. Okay, x, y, z coordinate system. Okay, yeah. Then here maybe is n hat, and here probably is n hat. Okay, yeah. So which one would you call its upward n hat? This guy here, right? Why would you call this? Because you see this guy here, if you decompose this one, it's going to have a z direction, a positive z direction component. Does that make sense? Right? You look at this one here, it's going to have a positive z direction. So this is basically what we call this is upward here, right? Upward. Okay. And for closed surface S, okay, for closed one, and what we do is we use so-called the outward, okay, the outward n hat, okay, as this positive one, okay, yeah. So we use outward here, okay, n hat. So when n hat is pointing outward for closed one, that's what we're going to choose as so-called positive direction. Okay, yeah. Okay, so once we decided on this now, okay, now let's take a look at different cases in terms of evaluation of this asset here. Okay, yeah. Now, first of all, before we talk about, let's take a look at a simple case. Let's take a look at a very simple case. We have vector field F, which is x, y, z. Okay, there's a vector field F here, and then we have a sphere. The surface is a sphere. X squared plus y squared plus z squared equal to a squared. Okay, so that's a sphere. Now we are interested in the flux. Okay, across this surface. Okay, so write down the formula again. Just remember the formula here. Because our surface is closed, so I'm using a circle here, okay, to represent this surface integral. F dot n hat dA, right? dA. Okay, that's what we're going to try to calculate. Okay, so we already have F. Okay, now the question is, probably let's take a look at what's n hat, right? What's n hat here? So n hat is determined by the surface. So your surface is a sphere. Okay, yeah. So what will be the n hat for the sphere? If you calculate using the gradient, what would you get? Okay, this is the sphere, right? The sphere. Yeah, well, first of all, what is the gradient of that guy here? Let's see, I'll use a W equal to this, okay? Yeah. Now what will be this gradient? Del W is, yeah. Okay, that's right. Then unit normal vector will be n hat is del W over this guy, right? Over this. So 2x, 2y, 2z over the magnitude of this guy here, which is what? Magnitude is 4x squared, 4y squared, 4z squared. Okay, yeah, that's magnitude. So there's a common factor 4. You take it out of 4. A square root of 4 is 2. So 2, 2, 2 got cancelled. So this guy equal to x, y, z over root x squared plus y squared plus z squared. Okay, yeah. So we're talking about this. We're talking about the unit normal vector on the surface here. Okay, at anywhere on the surface. So at the surface, what is the value of x squared plus y squared plus z squared? A squared, right? a squared. So this guy which is what? 1 over a x, y, z. Okay? Yeah. So that's the uninormal vector n hat. Okay? The other way of getting this one here is actually quite easy. If you have, this is a point, if you're interested in this point, it's a uninormal vector. Now if I create a vector from here to here, okay, because it's a sphere, so you know that what? You know this guy here, the reading line here, or this vector must be perpendicular to the surface, right? Yeah. So this is, if this is P, okay, so then this OP must be perpendicular to this S. Okay. If OP is perpendicular to this S, and then A n hat will be just OP over absolute value for OP, right? Yeah. And absolute value of OP is basically 1 over A, right? Because this is the radius. Okay. So X, Y, Z. Okay. Same results. Okay. That's here. Okay, so now you got n hat. Okay, now I'm gonna plug in this n hat over here, and then use the f vector dot this n hat. Okay, yeah. So what's the f vector dot n hat over here? Okay, so f vector is x, y, z, and n hat is this. So when you use this vector dot this vector, you then carry it out, it becomes x squared plus y squared plus z squared. Okay. Then divided by a, right? Yeah. And x squared plus y squared plus z squared equal to a squared. So this whole thing equal to a, right? Yeah. So that's pretty convenient. So this vector field's dot product with the unit vector give me a scalar value a. Then the surface integral, okay, which is basically becomes, okay, surface integral s and a dA. Right, ADA, okay, ADA. And A is a constant, so you can take the A out of this integral here, okay, out of this integral. So the only left with the dA, and surface integral dA. So what does this mean? This basically means the surface, the area of the surface of this sphere, right? Yeah, and that you have a formula, which is A multiplied by 4 pi. 4 pi a squared. Okay. Yeah. So overall, this is 4 pi a cubed. Okay, for this surface integral. So this gives you a sense of how you would calculate this flux. Okay. Yeah. How do I what? Here, left. Oh, I mean here. Oh, here. Oh, I see. So F is x, y, z. Dot x, y, z. 1 over a x squared plus y squared plus z squared. Okay, 1 over a squared. Yeah. Okay, now the only question here is, things are not so beautiful or so convenient all the time. Let's say if I change the f to a different vector field. If I change the f to let's say 0, let's say to z key hat. If this is my vector field, okay, if this is my vector field, if I do the same thing, and I will get f dot n hat, okay, which is basically z squared over a here. Okay, so I got z squared over a. So then if I plug this one into my surface integral, and I would get, okay, z hat over a and dA. Okay, yeah. So I guess now you can't do any simplification now, right? There's no trick or shortcut to do. Okay, so this basically the case. How do I evaluate this kind of case? This is basically the general things we're talking about here. Okay, yeah. Okay, so this is basically the next topic here, evaluating. So how do I calculate this one? Evaluating this surface integral. Okay. First of all, okay, you should not panic here. Oh, that's brand new things, right? as you're going to see, a surface integral will basically become a double integral. Okay, so if you're very comfortable with double integral, then the surface integral is no difference from a double integral. The only step is what I'm going to show you here. How do I set up the properly from this guy into a proper double integral format? Okay, yeah. Okay, so basically this is going to be a double integral. So as I said, you know, what we are doing, right? We're doing in 3D. Okay. So in 3D, what we learned, you know, we can use x, y, z Cartesian coordinates to represent this 3D here, right? Or we can also use cylindrical coordinates, which is r, theta, z, to represent this 3D. Or maybe we can also use the spherical coordinates rho, phi, theta, right, to represent this one here. Okay, but either way, you have how many variables? You have 3 variables here. Okay, yeah. But surface integral is a double integral, so basically you only need what? 2. Okay, so when you integrate, you only need 2 integrals, 2 variables to integrate over 2 variables there, right? Yeah. So in other words, we don't need to use all 3 here. We only need to pick 2 out of these 3. Okay, either x, y, or r theta or r z, right? Depends. Okay, yeah. So for example, if I'm talking about this guy here, okay, this guy, okay. So this is a sphere. If I use rho, phi, theta, okay, to represent the coordinates in this guy here, right? Now what we're integrating? We're integrating over where? Over this surface here, right? So think about any point on the surface here. What would be a constant variable in terms of 3 things? The rho, right? So basically, in this particular case, the rho will be a constant. Rho is this RA at here. So the only 2 unconstant ones, or the varying ones, is phi and theta. Okay. So in other words, you know, when you do this integral here, okay, you're actually not integrating over rho, phi, theta, everything like that. You can only integrate over the phi and the theta. Okay. So basically, in that particular case, that dA, okay, can be represented using d phi, d theta, and of course, maybe there's going to be something at here. Okay. Yeah. So that's basically the idea here. So once we're able to figure out this guy here, okay, once we're able to figure this out, and the rest of the job is basically a typical double integral. Okay, yeah. So now let's take a look at specific cases here. How do I basically single out this dA, okay, in terms of the variables that we need, right? So let's look at this spherical surface first. So case number 1, when you have a spherical, okay, surface. Okay, when you have a spherical surface. So that's basically the example that I just showed you there, right? Yeah. So when you have a spherical surface, okay, and in this particular case, the rho would be a constant. Rho would be a constant here. Okay. And we're looking for basically what's the dA, right, equal to. Okay. Yeah. So if I draw something out, I'll show you what it is, but I'm not going to draw it here. I think this is not that important. Okay. Okay. So here's a surface here, basically, right? We're looking for a small area on the surface of the sphere. Okay. So we're looking for how do I properly represent this small area using the variable phi and theta and the radius of the A. Okay. Yeah. So in the end, you'll get this one here, but let me write it down here, and then I'll explain what where this is from here. Back. So A squared sine phi, okay, delta phi, delta theta, okay, delta phi, delta theta. So that's the delta A, or small area, okay, on the surface of the sphere, right? Okay. Now before we use this one, you know, if you remember in triple integral, how did you get the dV? And what would be the expression for dV using spherical coordinates for a volume dV, which is what? Yeah, rho square. That's right. d rho d phi d theta, right? Yeah. See, now you're not concerned with a volume. You're concerned with a small surface, okay, on the small patch on the surface of the sphere, okay. And as we said, rho is going to be constant. Rho is rho is a over there. So you're not concerned with this d rho. So you're not integrating over the d rho here. So this is gone. And then you change that rho to a square. This is how you get that part there. Okay? Yeah. So basically, dA equal to a square, okay, sine phi d phi d theta. Yeah. So if you're very comfortable with the spherical triple integral in spherical coordinates, then when it comes to this, so dA here for spherical surface, okay, it's going to be this, right? Yeah. Is that good? Yeah. And of course, I think you need to know what is the relationship between x, y, z and rho phi theta. That's not going to change. Okay. But we're not talking about the x, y, z in 3D space everywhere. We only talk about the x, y, z at where? On the surface, right? On the surface. Okay. So in 3D space, if it's everywhere, it's rho, right? Sine, phi, and cosine theta, right? But I'm not talking about everywhere, so I'll just change the rho to a. Okay, that's basically the x, y, z on the surface of the sphere. Okay, so of course y would be a sine phi and sine theta, and z would be a cosine phi. Okay. And the phi and the theta, there's no change. The phi and the theta is the same definition as before. Okay, so the phi is the angle, right? The phi is the angle between this reading line and the z-axis, right? So it goes from this z to there. That's how it goes, right? And theta is the angle from x-axis to the projection of that in xy plane. Okay, yeah. And phi angle cannot go over pi. Basically, phi, the limits of phi is always 0 to pi. Okay, that's maximum, right? Or minimum 0, maximum is pi. Depends on the surface. Okay, yeah. And theta, of course, the maximum minimum is 0 to 2 pi. Okay, yeah. Okay, so now we're pretty much all set here, right? Pretty much all set. So the surface integral, when you're integrating over spherical surface, right? You can write, okay, this f dot n hat dA. Okay, that's the surface integral. Okay. Not necessarily going to be a closed surface, maybe just part of the spherical surface, right? So in general, I'm not writing a circle right here. Okay. So how do I convert this one here in the spherical coordinates? So then basically what happens is, if you remember, f, okay, basically is m and p, which are function of x, y, z. Now what you do is you're going to replace those x, y, z over here with this. Okay, yeah. So if I write it down just a little bit here, right? So f is m n p dot n hat. Okay. So now, yeah, it comes the question now. What is the n hat then? So we're looking at a sphere. So we're looking at a sphere centered around the origin. So as we just did, what's the n hat? This is a here. The radius is a. Yeah, in the direction phase. This guy here, right? We just did. Okay, that's n hat. Okay. So the n hat here, I'm gonna just replace the n hat with 1 over a x, y, z. Okay. And the dA at here, okay, dA. Okay, that's basically the setup here. But we don't need to use x, y, z because we're using spherical coordinates here. Okay, so then the next step is a slight change in here. We're going to replace those x, y, z, and also the x, y, z in the function m and p with x, y, z over here. Okay, yeah. So this is a bit of a long expression, but I guess if I write just slightly, just in short, it's going to be m. Okay. You know what? I'm not going to write it anymore. Yeah, I will just write m. There's this there's 1 over a here. Okay. Where's the 1? Yeah, 1 over a over here. mx plus ny plus pz, and dA, right? You change that to a squared sine phi d phi d theta. Okay, so this is dA. Okay, it's dA here. And this guy is the product, the results of this dot product, right? So dot product. So there's 1 over a here, there's a squared over here, so this a cancel that. Okay, so that equal to mx ny pz, and this that p multiplied by z, and a sine phi d phi and d theta. Okay, yeah. So how do I do with this term here? Right, that's what I said. Okay, replace x, y, z. Okay, with what? With those equations started here. Okay, with that stars. Right. That's what you do. That's it. Right? After you do this, then you only have 2 variables. One is phi, one is theta. And all you need to do is carry out the double integral now. Okay? Was that clear? Yeah. So take a second look at this thing here. Right? Yeah. So I guess now you probably should ask, so how do I know the limits for the phi and theta? So how, the question is this, then the same question is, how did you find the phi and theta when you do the triple integral? No change. Okay, same way as you did in triple integral, right? Same way. Okay. Yeah. So how do I find the phi? If you're given the surface, draw a line out of it, then find the angles of the reading lines, the bounds of the surface, right? On the surface. Okay. So if this is a complete sphere, then the phi will be from 0 to pi, and the theta will be from 0 to 2 pi, right? Yeah. So it depends on the sphere. Okay, then you determine the limits of phi and theta. Okay, yeah. Any questions? Okay. Yeah, let's take a look. Let's look at example here. Okay. So we'll finish the example that we left over there. Here's f vector, okay, z k hat, okay, and then we're having the sphere x squared plus y squared plus z squared equal to a squared, okay, equal to a squared. Yeah. Okay. So then what we do is we're going to use this spherical coordinates. Okay, so the surface integral. Surface integral. Now I use this because it's a closed surface. Okay. So f dot n hat dA, okay, is equal to, as we just derived, z squared over a and dA. Right. That's what we derived in the previous example. Okay. Now I'm going to use spherical coordinates now. So what do? I'm going to replace the z with which one? With this guy here, right? With this a cosine phi. So a cosine phi squared here, okay. And then dA is a squared sine phi d phi d theta. Okay, that's the dA. And limits for the phi and theta, since this is a closed one, right? So phi will be 0 to pi, and theta will be 0 to 2 pi. Okay, yeah. So that's not bad integral here. there is just one little trick substitution you need to do. A cancel this, A, so A squared, so you have A cubed. And cosine phi squared, sine phi, d phi, d theta. Okay, so this sine phi d phi here is basically d cosine phi. Okay, and put a negative here because d cosine phi is negative sine phi d phi. Okay, and then d theta. So inside here, this is cosine phi cubed, so you're going to end up with 1 over 4 cosine phi to the power of 4, right? Yeah. Okay. Did I got it right? Oh, this is square, right? Yeah. Yeah, square here. Yeah. So you do the calculation, huh? You end up with 4 over 3 pi a cubed. Okay. So you have a positive flux out of it. Actually, the results is the same as the volume of the sphere, right? Yeah. Any questions? Yeah. So that gives you a sense of how to calculate this one here. Okay. So now you look at this. The way to calculate this, the surface integral. Okay. The key step, right? The key step here, okay, is this step. Okay. So lay down the surface integral in terms of phi and the theta. Okay. And then the rest of the job is the same thing as calculating a double integral. Okay, yeah. Okay, so that's good. Now let's look at the second case now. Okay, so this is a first case when the surface is a spherical surface. And the second case is also less a special one here. Let's say maybe what we have is a plane surface. Okay, so for example, z equal to a. That's a plane. Okay, that's what we're talking about. So it's a horizontal plane. Okay, parallel to the xy. Yes. Yep.
Does that mean that the flux is going to be increasing as the radius increases?
Yes.
That just seems like, I don't know, I'm thinking like from like when you have a electron or whatever, like inside a sphere, like a point charge.
Yeah.
Like it's originating inside the sphere, so like.
Sure, but this is not a point charge. Basically, how much flux going through the surface depends on the vector fields, right? So you look at this vector fields here. That's not a point charge field, electric field. So if you draw this field out, right? Draw this field out. What does it look like?
Okay.
Right? Yeah. So you see, this is Z here, basically. That's okay. Let's think about this. This is actually a good question. So if you think Z here, at Z equal to 0, basically on XY plane, the field is 0, right? And as Z going up, so the field basically start to increase. Okay? Yeah, depends on the Z value. At the bottom here, Z is a negative value. So at the bottom, the field goes down. See that? Right? The field goes down. So now what you have here is a surface, spherical surface. And we're looking for the outward, basically we're looking for the outward flux, right? You see, there is outward here, there's outward here. So that actually explains why you got a positive value over here, right? Why you got a positive, okay? Yeah. Because definitely there is positive something going out of the surface here. Does that make sense? Yeah.
This vector field, is it just one vector basically from the origin up and down the x-axis, or is
everywhere?
There's vectors everywhere?
Everywhere, yeah. So basically you plug in z equals, you know, because yeah, so let's see, right? Let's say at location of 1, 1, 1. Okay, at location 1, 1, 1. What is my vector field at location 1, 1, 1? It's 0, 0, 1. Right? So you have at this location, you have an upward a vector like this. Yeah. Is that good? Yeah. So basically, I think it's good that you think of this way. You think you need to have a general thing here. You're talking about flux across the surface here, right? So, I mean, the flux in general basically something flowing here. And the surface is something like this. Now if I ask you, so then what determines the amount of flux across this surface? What matters? Surface area. What else? Flux density. So okay, flux density basically means the basically, you know, how fast it's going through it, right? Or how strong it's going through it. Okay. Anything else? You need to think about in terms of this one here. And n hat. So basically, it's also determined by the orientation of the surface here, right? And the banana is falling over this way, so but if you're trying to catch this way, not much is going through, right? Yeah. So you gotta hold it right, yeah, to catch the most. Okay? Yeah. Okay, so now let's look at this second case here, the plane surface, z equal to a. Okay? Yeah. Okay, so this is z equal to a surface here. And apparently, if I are looking at the unit vector to this surface, n hat, which will be what? Z we use, what do we call that? What do we call the unit vector in that direction? K, that's right. Okay, K hat. Okay, yeah. And you got a K hat now, and we're looking for, this is a dA at here, okay? Small area here. So because this is parallel to the xy plane, so that dA must be dx dy. Okay? Yeah. So that's it. That's basically the layout of this surface surface integral now. So this surface integral S, okay, n hat dA, okay, dot here, and that will be, okay, F is m n p. Okay, dot n hat is a k hat, so k hat meaning is 0, 0, 1. Okay, 0, 0, 1, and dA, dx, dy. Okay, dx, dy. So overall, okay, you what you get here is, okay, so this is m by 0, n by 0, p by 1, so there's only p left. So p, only p term, and p is a function of x, y, z. However, right now, where's the surface? At the surface is z equal to a. So the z quantity here is replaced by a. Okay. Then dx, dy. So now you see, this is basically a double integral, right? Where am I integrating? We're integrating over the projection of this surface in the xy plane, right? The region that you're looking at. How do I find xy limits? Same thing as a double integral now, right? Yeah, so no trick. Yeah. Okay, so this is basically the setup when the second case is presented. Okay. Now, if you're talking about this plane surface, not z equal to a. Let's say maybe you're looking at is a plane parallel to the xy plane. Maybe you're looking xz, that'll be y, right? Maybe is y equal to b, let's say, right? If you're looking at a plane of y equal to b. So this is a plane parallel to xz. Okay, this is a plane parallel to xz plane. Then similarly, you can try the same thing here. Then in that particular case, the n hat will be the g hat. Okay, and then the dA will be dx and dz. Okay, yeah. So if you're looking at x equal to c, so n hat will be I hat, dA will be dy dz, right? Yeah.
So we can make three lines related to that
Come again? When what? Yeah.
So we only constrain the field line which is going at the plane, the exact plane.
We only. Sorry, I didn't understand.
Can you draw the plane?
Here.
The exact
Z plane.
y equal to b.
Oh, y equal to b. I see. This is y, right? And this is b here. That's y equal to b plane. Yeah. Okay. Oh, by the way, actually, you probably should ask. See, it's here, right? I have a surface here. I got two directions, right? I could have an n hat as a negative k hat, okay? But I'm using k hat here, all right? Because we want it to be, the up one is usually what we call the positive direction, okay? However, okay, but you need to also be aware, okay? Actually, in the next lecture, you'll see that in certain cases, you do need to calculate the surface integral or the flux, the total flux going down of this surface here. All right? Yeah. So what I'm saying here is when you use this one dot the positive 0, 0, 1. So this surface integral, what they give you is the net flux going upward. Okay, that's the calculation. Is this going to be a positive value for sure? We don't know, right? Yeah, maybe it's going to end up with a negative value. And a negative value just means there is no positive flux going upward through the surface, right? It's the net flux is actually a negative value. Okay, yeah. Okay, so that's the case number 2. I think I'm going to skip myself an example here. So it's just so simple. So I'm going to look at the case number 3. So case number 3, as you can guess, is going to be a cylindrical surface. Okay, cylindrical surface. So cylindrical surface basically means you have a cylinder sitting at here. Okay, and your concern is what is the net flux out of this, okay, the cylindrical surface here. Okay, now make sure right now, okay, there is no surface over here at the top and the bottom yet, right? Yeah. Okay. So as a matter of fact, okay, if the question is slightly changed, what is the flux? Let's say, for example, I have a cylinder like this here. What is the flux out of this cylindrical object surface? Then actually now, how many surfaces do you have? 1, 2, 3, right? You can have 3 different surfaces. But for now, all I'm concerned is what is the flux out of this, the around side here, right? No, only for that part. Okay. Okay. So if that's the part we're looking at, so we're gonna basically talking about the 2 things. What is the n hat and what is the dA? Okay. Now once we figure these 2 out, okay, and we'll be okay. Okay. Well, let's look at this simple case here. Let's say suppose the bottom here is x squared plus y squared a squared. So that's a cylinder, huh? That's a cylinder. Yeah. So if this is x squared plus y squared equal to a squared, and the n hat is a direction, okay, normal to the surface of the cylinder, okay. Then imagine this, right? When you look from the top, okay, when you look from the top. So everywhere is a circle, right? Everywhere is a circle. And the n hat, basically it's the vector perpendicular to the circle, right? The circle here. Okay? Yeah. And what would be the uninormal vector for the circle? Which would be what? 1 over a, exactly. X, y. Okay? That would be this. And now we're talking about dA. dA is an area, okay, it's a small patch, okay, on the side of the cylinder, okay, on the side of the cylinder. Well, I think I'm going to use the similar idea here. If I'm talking about the volume, okay, d volume of a cylinder using cylindrical coordinates, what did we derive? We derived the r dr and dz dc, right? Yeah. Okay. Now the thing is, here you have a cylindrical surface. You're not concerned with anywhere. You're only concerned with the points on the surface. So the points on the surface basically means we're not concerned with the dr. So the r we're not changing. And the r here is a constant. So this a here will be just simply a and dz and d theta, right? Yeah. So that's basically dA at here. Was that clear? Yeah. That's it. That's the in hand, that's the dA, and you figure out this two key information, you plug it into this surface integral formula, right? And then you're ready to do the calculation. Yes, Simon. Not necessary. Yeah, we can. That's going to be limited by basically the z, right? Yeah. If it's between, let's say, -1 to +8, then z goes from -1 to 8. Yeah. However, for the current case, there is a constraint though. The cylinder has to be centered around the origin at here, right? Yeah. If the cylinder is not centered around the origin, we're going to have to use a so-called the transformation of the variable using the Jacobian to transform that to the origin first, right? Yeah. Actually, one of the questions I raised up on the Piazza, nobody bothered to answer, and I haven't either. So that was a question basically needs to use the transformation of the variable, right? Yeah. Okay. So once we figure this out, then the surface integral, okay, is going to be m n p dot 1 over a x y 0. Okay. dz is a dz d theta. Okay, so that's the surface integral, and this a cancelled, and then the dot product, there's a 0 there, that's great, and we have mx plus ny, okay, and a dz d theta. Okay, yeah, dz d theta. So what do we do with this x and y here? So we replace x with a cos theta and y with a sine theta, right? And z we don't do anything, so z is just a z, right? So then once you do the replacement, then this whole chunk at here, right? This whole chunk at here will be only a function of the two variables, which is the z and the theta. And now you need to figure out the limits for the z and theta based on the cylinder, the cylindrical surface. And that's basically a typical double integral problem, right? Yeah. Okay, that's it. Any questions? Yeah. Oh yes, they cancel out. Good point. Thank you. Okay. Okay, so let's take a look at one example, and then we can. We may not have time for further, but so let's take a look at one example. All right, so here is F, here's S. And the Z between 0 and 1. And what will be the surface integral? Okay, yeah. So, it's quite easy actually. F, x, z, negative y, dot n hat. N hat is determined by the circle at here. So the radius is 1, so there's 1 over 1 is 1. So x, y. Okay, x, y. And dA is a dz d theta. A is 1, so just the dz d theta. Okay. Yeah. The z quantity is going to change from 0 to 1, and the theta is going to change from 0 to 2 pi. Okay, that's a cylinder, right? Yeah. Okay, so then we're going to calculate this guy, but we have to do the dot product first. So what do we get? The dot product here end up with x squared. What's that? Yeah, this I missed the 0 here, right? Okay, x, y, z. So x squared plus zy dz d theta. And change the x to r cosine theta square. Now r, change that to a, right? And a is 1, so that's just cosine theta square. And y is sine theta, and z is z. Okay, was that right? Yeah. Okay, so then the next thing is just typical integral here. Okay, there's no trick here. But yeah, there might be a little trick at here. Okay. So just in case, right? So let me write down this guy here. Okay, so this is what comes out. Okay, this is what comes out from this this step here. Okay, inside here the z, there's only one z here, so the z becomes 1/2 z squared. Plug in the limits. That's where your 1/2 at here shows up. Okay, yeah. So I guess this is simple here. Okay, so the only part in this part here, some student maybe will need a formula or something. So what's cosine theta squared? It's this. All right, it's this. So you can do, if you convert this one into this, and you will be able to carry out this integral, right? Yeah. And of course, you had to change this small substitution at here. Okay, let u equal to 2 theta, and then you can do it, right? Yeah. Was that clear? Okay. Yeah. So overall, it is going to be equal to pi. Okay. Okay, so that's cylindrical. I have one more case here I'm not going to cover anymore, which is basically a general surface. Okay, so things are not beautiful, just the surface right there, right? It's maybe z equal to x squared plus y squared, that kind of case. So in that particular case, what will be the setup for the surface integral? That's what we're going to finish next Tuesday. Okay.